From the smallest grain of sand to the most distant star, everything we see around us is made of matter. But what is matter really made of? For centuries, this fundamental question has captivated scientists and philosophers alike. The answer, as we understand it today, lies in the realm of the very small, in the heart of atoms, where we find particles called quarks. Imagine a world so tiny that it's impossible to see with even the most powerful microscopes. This is the world of quarks, the fundamental building blocks of matter. They are so small that their existence was only theorized in the 1960s, a testament to the incredible advancements in physics during that era. The discovery of quarks revolutionized our understanding of the universe. It showed us that the atom, once thought to be indivisible, is actually a complex structure made up of even smaller particles. And at the heart of this intricate dance of particles, we find the humble quark, holding the key to the universe's most fundamental secrets. We are just beginning our journey into the strange and wonderful world of quarks. As we delve deeper into their properties and interactions, we'll uncover the secrets of how matter is formed, how stars burn, and ultimately, how the universe came to be. To understand quarks, we need to take a journey deep inside the atom, into a realm far smaller than the width of a human hair. Imagine shrinking down to the size of an atom. What would you see? At the center of the atom, you'd find the nucleus, a tiny, dense region that contains almost all of the atom's mass. If the atom were the size of a football stadium, the nucleus would be like a marble sitting right in the middle of the field. But the nucleus is not alone. Buzzing around it like tiny bees are the electrons, particles that carry a negative electric charge. The electrons are much lighter than the nucleus, and they exist in a cloud-like region that surrounds the central core. For many years, scientists believed that the nucleus was the smallest, most indivisible part of matter. But as our tools and techniques for studying the atom improved, we discovered that even the nucleus has a secret inner structure. In the 1960s, physicists began using powerful particle accelerators to smash atoms together at incredibly high speeds. These experiments, like microscopic demolition derbies, shattered the atom's nucleus, revealing its hidden components. The debris from these high-energy collisions pointed to the existence of even smaller particles within protons and neutrons, the particles that make up the nucleus. These building blocks, particles with a whimsical charm, were given the name quarks. The discovery of quarks was a watershed moment in physics. It meant that protons and neutrons, once thought to be fundamental and indivisible, were actually composite particles, each made up of three quarks bound tightly together. This discovery revolutionized the field of particle physics, leading to a new understanding of the fundamental constituents of matter and the forces that govern their interactions. It was the beginning of a new era, one in which the quest to understand the universe on its smallest scales would continue to drive scientific exploration. The world of quarks is full of surprises. For one, quarks come in 6 different types, which physicists, with a touch of whimsy, have named flavors. These flavors are up, down, charm, strange, top, and bottom. Don't let the whimsical names fool you. These quarks are serious business. They are the fundamental building blocks of matter, and their properties determine the characteristics of the particles they form. Each flavor of quark has its own unique set of properties, such as mass, charge, and spin, that distinguish it from the others. Up and down quarks are the most common and the lightest, forming the familiar protons and neutrons in the hearts of atoms. The other 4 flavors, charm, strange, top, and bottom, are heavier and more exotic, only observed in high-energy collisions. Section 5. Up and down quarks. The everyday variety. Up and down quarks are the most common and the lightest of the 6 flavors, and they are the ones responsible for forming the protons and neutrons that make up the nuclei of atoms. In essence, they are the quarks that make up the matter we experience in our everyday lives. The up quark carries an electric charge of +2/3, while the down quark carries a charge of -1/3. These fractional charges are a unique characteristic of quarks, and play a crucial role in determining the overall charge of protons and neutrons. A proton, for example, is made up of 2 up quarks and 1 down quark. Adding up their charges, +2/3, +2/3, and -1/3, gives us a total charge of +1, which is indeed the charge of a proton. Section 6. Charm, strange, top, and bottom, the exotic cousins. While up and down quarks are the workhorses of the everyday world, their heavier cousins, charm, strange, top, and bottom, are no less important. These exotic quarks are much heavier than their up and down counterparts, and they are not found in ordinary matter. Instead, they are produced in high-energy collisions, such as those that occur in particle accelerators or in the extreme environments of supernova explosions. These heavier quarks are unstable and decay rapidly into lighter particles, making them difficult to study. However, their fleeting existence provides valuable insights into the fundamental forces of nature and the early universe. The discovery of these heavier quarks was a triumph of experimental and theoretical physics, confirming the predictions of the Standard Model and opening up new avenues of research into the fundamental nature of matter. Section 7. Quarks have properties to charge, mass, and spin. Like any other particle, quarks have intrinsic properties that define their behavior. Three of the most important properties of quarks are their electric charge, mass, and spin. We've already touched upon the electric charge of quarks, which is a measure of their interaction with the electromagnetic force. Quarks carry fractional electric charges, either plus 2/3 or minus 1/3 of the elementary charge, which is the charge carried by a single proton. Mass, on the other hand, is a measure of a quark's resistance to acceleration. The heavier the quark, the more difficult it is to change its velocity. Quark masses vary widely, from the light up and down quarks to the massive top quark, which is about as heavy as a gold atom. Finally, spin is a fundamental property of particles, like a tiny internal spinning motion. Quarks have a spin of 1/2, which means they are classified as fermions, a category of particles that includes electrons and neutrinos. Section 8. The strong force holding quarks together. If quarks have fractional electric charges, why don't we see them flying around freely? The answer lies in a fundamental force of nature called the strong force, one of the 4 known fundamental forces in the universe. The strong force is responsible for binding quarks together to form protons, neutrons, and other composite particles called hadrons. It's an incredibly powerful force, much stronger than the electromagnetic force that governs the interactions between charged particles. The strong force acts over extremely short distances, within the confines of the nucleus. It's like a powerful glue that keeps the quarks trapped inside protons and neutrons, preventing them from flying apart. Section 9. Color charge. A different kind of attraction. The strong force, however, has a peculiar characteristic. It doesn't just depend on the distance between quarks, it also depends on a property called color charge. Now, don't be misled by the term color. Quarks don't have colors in the conventional sense. Instead, color charge is a quantum property analogous to electric charge, but instead of positive and negative, it comes in 3 types: red, green, and blue. Just like with electric charge, opposite color charges attract. A red quark will attract a green quark and a blue quark. This attraction is what binds quarks together in groups of 3 to form hadrons. Section 10. Quarks in confinement, never alone. Here's where it gets even more interesting. The strong force doesn't allow quarks to exist alone. They are always confined within hadrons, either in groups of 3 or as quark-antiquark pairs. This phenomenon is known as quark confinement. Think of it like this. Imagine trying to pull 2 quarks apart. As you pull them further away, the strong force between them gets stronger, like stretching a rubber band. Eventually, you'd put in so much energy that a new quark-antiquark pair would pop into existence from the vacuum, and you'd end up with 2 hadrons instead of 2 free quarks. This confinement of quarks within hadrons is a fundamental aspect of the strong force and explains why we never observe free quarks in nature. Section 11. Quarks, unlocking the secrets of the universe. The discovery of quarks and the understanding of their interactions have revolutionized our understanding of the universe. These tiny particles, once just a theoretical concept, are now recognized as the fundamental building blocks of matter. From the nuclei of atoms to the cores of neutron stars, quarks are everywhere, playing a crucial role in shaping the cosmos as we know it. By studying quarks and their interactions, we gain a deeper understanding of the fundamental forces that govern the universe, from the smallest scales to the largest structures. The journey into the world of quarks is a testament to the power of human curiosity and our relentless pursuit of knowledge. It's a journey that has taken us deep into the heart of matter, revealing the elegant and intricate workings of the universe at its most fundamental level. And as we continue to explore the strange and wonderful world of quarks, we can be sure that even more exciting discoveries await us. discoveries that will continue to reshape our understanding of the cosmos and our place within it.